It is about work that's in progress with all four of these people. And let me just say that maybe for a broader audience, let me introduce the subject of complexity in just a few sentences. So this is about the AdS CFT correspondence. And here I drew for you a cylinder, which could be maybe pure anti-de Sitter space or maybe anti-de Sitter space with some matter. We typically represent it as a cylinder. And I highlighted the spatial slice of that AdS space. On the side of it, I drew a Penrose diagram for a two-sided black hole. And if I just slice through it at different time slices, then what I get is a geometry that looks like this, if I actually represent it. Or if I slice through it at some different time, then I get a geometry that looks like this. And it is not an accident that I drew one of them as shorter and the other one as a longer one, because these slices tend to grow with time. And so in 2015, Lenny Susskind proposed that, or first of all, he asked the question, if these equal time slices of the geometry are growing, and if we believe in the AdS CFT correspondence, which tells us that everything that happens in an AdS gravity theory, which has a holographic dual, everything there should have a counterpart in the conformal field theory. So if we believe that, and something is growing in AdS space, then something must be growing in the CFT. And what is that? And more or less by definition, he defined whatever it is to be state complexity. It wasn't exactly just a definition. He said that he had various reasons to believe why this quantity shouldn't be called something else, but actually state complexity. I will not go into those arguments in detail, but suffice it to say that there is a conjecture out there, which is that the growing spatial sizes of spatial slices, first of all, and sizes of those slices in anti-de Sitter space correspond to growing state complexities in the CFT. And I want to make a remark here. I even drew a little glass here. It's not AdS space. This is a glass which is half full, half empty. And so let me make comments about this correspondence, which are the pessimist and the optimist version of, opinions on it. So the pessimist would say, neither side here is well defined. What do you mean by spatial sizes anyway? And on the other side, what do you mean by state complexity? This is a pessimist speaking. An optimist says there is opportunity here because these definitions are flexible and they are waiting for our creative input. And so I am going to take the optimist's perspective and say the two sides of this correspondence are not really well defined, but we need to be creative and define both of them appropriately so that the correspondence is not only true but well defined. It's up to us to define it well. But let me just summarize what proposals have been made thus far. So the two, and because we're making a correspondence between two different things, between two sides of the duality, there are really proposals on both sides of the duality. So on the AdS side, the two leading proposals are the maximal volume spatial slice proposal. So here I drew a little cylinder and I marked some spatial slice of it, and the volume of that is conjectured to be, by Susskind et al. Actually, to be the complexity of the state. Then another proposal also by Susskind is that out of this spatial slice, you form a region which is time-like separated from every point on the spatial slice, and this is called the Wheeler-DeWitt patch. Now this is a codimension 0 subregion of AdS space, unlike this, which was codimension 1. And since it's codimension 0, it makes sense now to evaluate the action in it. So the proposal is action in the Wheeler-DeWitt patch would be the complexity on the AdS side. Now on the CFT side, there are also various proposals for what complexity may mean. And those proposals include circuit complexity or distance in the Fubini study metric in Hilbert space. There's also a proposal about path integral optimization. And there are other proposals that I'm not listing here, but there's many of them. And I'm really just listing them here to give you a sense that there is no consensus about what we mean by either side of this proposed duality. And there's definitely room for one more proposal. And ideally, a proposal should have the feature that it is well defined on the CFT side and it evaluates to something reasonable on the AdS side. The problems with the proposals that are currently there is that they are well defined on one side, but, yes, they are well defined on one side, but then we don't know how to make contact with the other side. So they're kind of ad hoc from one side of the proposed duality. So an ideal proposal would be one that's well defined in the CFT, and then you could evaluate it in the bulk and it gives you something nice, which actually corresponds to spatial sizes in the holographic geometry. Okay, so before I go on, let me just give you one more preliminary about complexity, which is that it necessarily depends on the cutoff. And so here is a quick reason why. Here I drew what the holographic proposals, the currently dominant holographic proposals in the bulk would tell you about complexity, the volume of a spatial slice, or the action in the wheel or the width patch. And both of them, strictly speaking, are infinite. And why is that? It's very easy to understand that a conformal field theory is a theory without any special scale. Now, the radial direction AdS corresponds to scale. The fact that the conformal field theory doesn't have any special scale means that there is, in fact, an infinity of different scales here as you go from the asymptotic boundary towards the bulk. Or another, maybe even more trivial way to say it is that the boundary of AdS space is an asymptotic boundary. It's infinitely far away. So this distance here is infinite. So whatever, and it's infinite because it represents all possible scales. So therefore, no matter what we mean by state complexity, it must be infinite if we're working in a true CFT without a cutoff, because whatever state complexity is, it's something about preparing the state, but that state has details that come in at every possible scale. And so there are infinitely many details to take care of if you want to prepare a state.
Can I ask a question? Yes. Then the argument will be that it's both infrared and UV divergent, or?
Well, the infrared divergence here, I guess, since I'm drawing a cylinder and not Poincaré AdS, then I think I only have to care about the UV divergence, but it's still there. If I was talking about Poincaré AdS and a CFT on a plane, then an infrared divergence would also be there.
Okay, thank you.
Another question. So are you going to take the point of view that the vacuum subtracted complexity is meaningful, or are you going to try to come up with a definition that's cutoff dependent?
I'm going to come up with a definition that's cutoff dependent. And I want to say that the only thing that makes sense really is cutoff dependent. Now you're asking, could I have just subtracted something from the vacuum? And that would be another way to proceed. So I will just not be doing that. And
actually, can I say one more thing? So in the definition of complexity, there's a room for a state, a reference state. So you're going to pick that reference state to be totally
no. So I'm gonna, I should have talked about this. So in this circuit complexity business, and also in the distance in the Fubini study metric, in these two approaches, the idea is that there is some reference state that is preferred, and then we're counting our complexity relative to that state, and that's what Nima is referring to. For example, in the path integral optimization, that reference is not there at all. And so we can debate whether a definition that depends on the choice of a reference state is a good definition. My personal opinion is that I don't like reference states. So if I can come up with a definition of state complexity that does not involve a reference state, I will be more pleased. And that's what I will do for you today. But anyway, it's not something that we should think is hardwired into discussions of complexity. It's an artifact of these two models of complexity that people tend to prefer. Did I answer?
Thank you. Thanks.
Yeah, sure. So, okay, so right now I was, the last thing I was about to say is that complexity is only well defined after we specify a cutoff, or some reference CFT scale. So yeah, a reference CFT scale is fine for me, but not a reference state. So here is the plan for today. The plan for today is that I will tell you a completely new idea for how to think about all of the things that we just mentioned. Starting from even state, I will tell you a new way of thinking about what a state is. Certainly, I will tell you a new way to think about what a cutoff is, I think. And most definitely, I will be telling you a new way to think about state complexity. And it's important to be organized. So let me emphasize where I am starting from. These are my logical starting points. Subregion duality, that's a statement that I will explain later, is definitely something that I'm assuming. Modular parallel transport, that is a concept that I developed together with Jan de Boer and Lampros Lampro, and also with James Sully and Sam McCandlish. That is something that I will explain later on in the talk, and that concept is an important starting point for this discussion. And then from computer science, really, I have an input in the form of a concept of query complexity, which is a different type of complexity, not circuit complexity, not, well, anyway, none of the previously discussed types of complexity, none of the types of complexity that have previously been discussed in the context of AdS CFT. It is, however, a type of complexity that is often discussed in the context of computer science. So yes, so these are my starting points. And maybe it's also important to highlight the biggest conceptual change. So let me just say it right away. I want to think of a state as an algorithm. That's what will allow the concept of query complexity to be applicable. I want to think of the state as an algorithm which takes as input an operator in the CFT, and then it performs some computation. That's what the algorithm does. And it spits out the expectation value of that operator in the state that we are discussing. This line that starts with operators and takes them to expectation values is what a state is. Are there any questions about this, way of thinking about what a state is? If there are none, then I'll go on. So this should be familiar to people with an information theory background, where we typically think of states as functionals on operators. On the other hand, if you have been mostly working on some on a heavily real physics type of area, for instance, nuclear physics, then in that case, probably this way of thinking is a little more exotic. But anyway, I didn't invent it. I'm taking it from an information theorists typically think of states as maps from operators to real numbers. And that's what we'll be using. And moreover, I want to think of a state as an algorithm which actually tells me how to compute those expectation values. And so I'll tell you in a moment how to make this precise.
So question?
Yes.
Given a set of operators and a set of expectation values, is there a unique algorithm that goes from one to the other?
Yeah, so it should be an optimal algorithm, and I'll give you an algorithm, and then we can discuss whether it has a chance of being optimal. And I think it will be pretty clear that it's optimal. Let's
sure.
We'll talk about it after I give you the algorithm. Yes. Okay. So
how about uniqueness? How about uniqueness? Say from one set of input to one set of output, whether or not the state you defined it this way is unique.
Well, I would say that if a state if two states have exactly the same expectation values for all operators, then they are the same state. And if you proceed more axiomatically, then you would say, suppose that there are two states that give me the same expectation value. Let's assume that they are pure states. Then I would form a new state, which is the outer product of state 1 minus state 2. And that would be a new operator which does not have the same expectation values in the two of them. So I guess that just shows that there is always going to be an operator that distinguishes any two states.
Mm-hmm.
Okay, so just to emphasize or to bring out a little more this way of thinking about an operator as first as a map, as a state, as a map from operators to expectation values. Imagine that we made a table where in one column we have just a list of all operators we'll ever use. Okay, operator 1, 2, 3, 4. And then in the second column, we would want to just put in their expectation values. And the statement that the person just asked about is, how do if I specify all these numbers, have I really specified the state uniquely? And the answer is yes. Now, I emphasized before that it's really important to talk about a cutoff. And so here's the way that a cutoff can show up here. Let's say that I managed to divide my operators in some way into two classes, the ones that are sensitive to physics below the cutoff and the ones that are not sensitive to physics below the cutoff. Then, so suppose that I made a division like this. Then we would say, oh, the operators that are strictly speaking in the UV past the cutoff, if we're talking about a state at the cutoff, then we don't need to specify these numbers. So a state at the cutoff is one that prepares these expectation values, but it does not prepare those expectation values. So that's a way of thinking about what a state at a given cutoff might be. So here I highlighted this. A cutoff restricts the domain of the map from operators to expectation values. And so the next question to ask is, how exactly do we specify these numbers? And the answer is that we always have to give ourselves an algorithm for computing them. So let me explain what I mean by an algorithm.
Sorry,
again, we're
question. So when you have operators below a cutoff, from an algebra perspective, like do they form a subalgebra or something, or a subspace?
Or
can we say something about that?
I think that if they are, I think that if maybe the algebra of, maybe operators that are coarser than a certain cutoff form an algebra, because it's hard for me to imagine how just starting from IR physics, I could generate some UV physics, but maybe I'm wrong about this, but that question will not be important for this talk, because them just forming a vector space and not an algebra is good enough for my purposes.
Okay, thanks.
Okay, so here is so the last slide was about a state as a map from operators to expectation values, but now I want to say that we actually need a little more than just a map. We specifically need an algorithm to evaluate the map. So here's an example of a state that we're very familiar with, which is the ground state of a CFT. It's specified by what? It's specified by some symmetries, and in particular, these three conditions specify a ground state of a CFT. So the way that we would usually compute correlation functions in the ground state is that we would use these symmetries, so these conditions, to apply them to the operators themselves. We would infer from that some transformation rules for whatever this correlator has to be, and those transformation rules specify 2-point functions and 3-point functions uniquely, and then the higher point functions are, as you know, dependent on the details of the theory through the OP coefficients and the spectrum. So that's what we do for the ground state. This kind of method is okay here, but it doesn't generalize easily to states that don't have any special properties like these symmetries. And so I would say that this method is a trick because this state is special, and the trick is hardwired for the special state that we're talking about, for the ground state. So I want to talk about general states and not just the ground state. So for this, we need an algorithm again, but an algorithm that's not trick-based, but something more robust. And so a better example to guide our intuition is a tensor network. A tensor network is literally an algorithm that computes expectation values of operators. As in, I just give you some tensor, I'm assuming here's some familiarity with tensor networks. So here's a tensor network. In this case, I drew a Mera tensor network, which prepares for me a pure state psi. Here is a tensor network, which prepares a pure state psi bra. And then this object, just the ket and the bra tensor network, has some dangling indices which are just waiting for operators to be put there. And the moment I put those operators, this whole object is going to contract as a tensor network to a number, and that number will be the expectation value. So if we think about tensor contractions as steps of an algorithm, that's exactly the kind of thing that I was talking about. And let me make a remark here, which is that oftentimes people who study tensor networks have this picture where there's a very big Hilbert space of states, but then they say, here's a very, very tiny corner of states that are actually relevant physically. And they say, these are the ones we want to capture with our tensor networks. So I want to say the whole big Hilbert space is like the space of all states, regardless of whether they can be, regardless of whether a nice algorithm can capture their expectation values. Whereas the physically relevant part of the Hilbert space is the one for which a sensible algorithm makes sense. So I'm just reinterpreting the words that are frequently used by tensor network people to say that what they really mean is a sensible physical state is the one for which we have some realistic hope of characterizing its expectation values. But that realistic hope would always be captured in the form of some algorithm, and that's what I'm talking about here. Are there any questions or comments about that?
So one question. The importance of tensor networks and this class of states is that they sort of this corner of the corner of the Hilbert space that corresponds to the states that they try to capture appear as low energy states of local Hamiltonians, right? So there's something special about them, right?
Yeah.
But are they gonna set restrictions on the type of algorithm? Because if you allow,
I'll give you an algorithm in a moment, and then actually all the rest of my talk is about specifying the algorithm. So then we can go back and ask, where is the reasonable behavior under where is the fact that they arose as states, low energy states for local Hamiltonians? Where is that buried? And so maybe we can talk about this as part of the questions after the algorithm is given. But I think my preliminary answer is that, so I told you about the various starting points that I'll be using. One of them is modular parallel transport. And the idea is that modular parallel transport, I think, would be a completely crazy thing for states that are not low energy states and for local Hamiltonians.
Thanks.
So I think that's where it's sitting. Okay, so let's, so I made this, I have one more slide of preliminaries and then we'll actually construct the algorithm. So the one more slide is about the query complexity of an algorithm. So what is query complexity? It's it's a measure of, or it's just the count of how many times an algorithm calls some special subroutine. So in the case of a tensor network, again, think of a tensor network as an algorithm. We contract this tensor network and it gives us correlation functions. And when we contract a tensor network, this is a sequence of basic steps which are contractions. And then it's natural to think of the sort of complexity of the tensor network as the number of tensor contractions you're doing. So I listed these three features here, and now let's try to be a little more general without making a commitment to the concept of a tensor network, use the language of algorithms. So I would say that the tensor network itself generalizes to just some algorithm for computing correlation functions. And the tensor contraction is that subroutine that you would be repeating as you are actually implementing the algorithm. And so the number of tensor contractions is the number of times you call a subroutine. That's what we call query complexity. So all this was meant to say that query complexity plays the same role for a general algorithm as counting tensors does for a tensor network. And let's examine a special case of this.
Since we're talking about the, I mean, just a naive, so in the computation part, purely computation, what are like typical examples of these? Like what do they use it for?
Sorry, you mean tensor contractions? Or
no, the query complexity, like is finding primes, I don't know, something, you know, what do they?
Yeah, actually, although I'm not really prepared for this, so I don't have a good flashy example for this, but
no, that's fine, yeah.
Yeah, so sorry that I didn't, but thank you. This is the first time I'm giving this talk in this form, so I will prepare an answer for this question next time. Yeah.
Can I ask you a naive question as well? There's also another notion, Kolmogorov complexity. Is that related to query complexity? Because that's also the length of a minimal optimal algorithm.
Sorry, did you say Kolmogorov complexity?
Yes.
Yeah. So that doesn't not really, because what if I mean, here is a Kolmogorov complexity of here is a description that realizes Kolmogorov complexity, the ground state of the simplest CFT, okay? And then the answer, simplest. Maybe I have to say a few more words. And then you would say, oh, okay, that's the ground state of the free boson. So maybe I have to be more rigorous about what I mean by simplest. But anyway, it's unlikely that this set of words, which specified for you a state, yes, uniquely, it's unlikely that this set of words has anything to do with volumes of spatial slices in any empty de Sitter space. Well, it's unlikely that this way of thinking will generalize in holographic context to volumes of spatial slices. So anyway, no, so query complexity is not like that at all. I have an algorithm for computing certain things, and then I'm just asking, maybe on average, or maybe in the worst case scenario, I'm not being careful about this here, just how many times I'm calling a certain subroutine in an algorithm. Completely different from asking what is the simplest description of some object. Yeah, Nima, is that okay?
Yes, thanks.
Okay, so good. So
sorry,
yes.
One more question. So in order to make analogy with the number of tensor contractions, are you making an underlying assumption that the algorithm is like iterative or recursive or something of that sort?
Am I making an assumption
so
that the algorithm
are you assuming that the algorithm is iterative or recursive or something of that sort when you say you're making multiple calls to the subroutine?
Yeah, the concept of query complexity assumes that there is some bottleneck procedure which such that if you just count how many times that procedure is done, that translates into how long the algorithm runs. Yeah.
Okay, I see. Thanks.
Yeah, so I just want to also clarify that I will not be talking about tensor networks in the remainder of the talk. Here, I just wanted to say that this new way of thinking I am proposing about query complexity and algorithms is not actually a radical departure from things that we have seen previously. All I'm trying to say is that tensor networks and tensor contractions were a special case of the thing that I'm just trying to be a little more general than things that people have already discussed before. That's the main point I'm trying to make with tensor networks here.
Can I make a small comment here? I think this relates to what I talked about last year, I don't know, about tensor rank. I think tensor rank is a measure of query complexity with the subroutine of the algorithm would be the multiplications. So I don't know if you guys remember my talk a while ago, but that would be an example of this, I believe. Just a small comment, sorry about that.
Thank you.
Thanks. So I'm not aware of this work, but let me quickly look it up, and then maybe I'll be giving it as an example in future editions of this talk. But okay, so and one more thing I wanted to say is that if you agree with me that counting tensors in a tensor network is really looking at query complexity for a particular kind of algorithm, which is a tensor network, then notice that we are extremely close. We're literally on the ball in agreement with the original motivation for what's called the volume proposal for complexity. So when Lenny and collaborators said that, I mean, when Susskind and collaborators said that initially, that complexity should be related to the volume of a spatial slice of a geometry, they imagined that there is some hypothetical space-filling tensor network, and then they said, oh, volume of space is like counting the tensors. And then they said, that's complexity. So they were basically saying complexity should be counting the number of tensors in some tensor network, which is a special case of query complexity. So again, the statement I want to make is that inspecting query complexity is being very faithful and loyal to the original motivation for even proposing the volume proposal in the first place. Okay, so today I will be telling you about, the statement I want to convey today is that state complexity is perhaps, or at least one version of it, is query complexity for the optimal algorithm that evaluates the map from operators to expectation values. And then I'll tell you what this algorithm would have to be. Now here is an example of our algorithm. So let's say that we are in the ground state of a CFT, which is the simplest example we can imagine. And now I will be in the ground state on a line, just to keep things simple because this is meant to be just an illustration. And so, and I will just be looking at an equal time slice of the dual geometry. So here's an equal time slice of the Poincaré patch of AdS3. And that's a picture we have. And imagine that I'm on a z equals constant slice in these coordinates. And suppose that I wanted to compute a CFT 2-point function on this cutoff surface. So what might I want to do? So I told you that opening DiFrancesco and just working from symmetries is not something that will generalize very well, but here is an idea that does generalize. So here I just wrote down a way in which we can compute the same correlation function in a more pedestrian and kind of pedantic way that generalizes. Namely, I'm going to just start with the ground state period, and then I'm going to compute the exponential of this object, where I'm going from infinity down to some x1 where my first operator lives. Then I apply the operator O1, and then I keep going with the same kind of exponential of some operator until I hit the second operator O2. And then I again apply this kind of exponential of some operator. And when I arrive at minus infinity, and take the bra also with the ground state. So what are we doing here? So this thing that we are integrating in this exponential is an operator valued 1 form. Yes, it has a dx in it, so it's a 1 form. It's operator valued because the 1 form is multiplied by an L-1, which is a special operator in the CFT. And the fact that it's an operator valued 1 form means that if I take an exponential, or generally a path-ordered exponential of this kind of object, it will integrate to a finite operator in the CFT. So an operator valued 1 form is something that if you take an integral and exponentiate it, it will give you an honest finite operator in the CFT. So we can, in this case, the operator that I'm taking is L-1 dx. And the reason why is that I want something that performs translations along my cutoff surface. And it's easy to see that in this context, in this special space, when I'm going along the z equals constant cutoff, the operator valued one form that I need is L-1 dx, because we're just doing horizontal translations, and L-1 generates translations. In general, when I go to further or different geometries, I will want to generalize. Yes.
Isn't L-1 generating null translations? Is that important or not? Or are you just?
So here I just, so L-1, by L-1 here, I mean L-1 plus L-1 bar. I mean,
Okay, sorry. I was just wondering whether
equal time spatial translations. So because we're on an equal time slice, we are effectively working with in the diagonal subgroup of the left moving and the right moving part of conformal symmetry. So every time I write L-1, I really mean an equal combination of L-1 and L-1 bar. If I wrote an L+1, it would be an equal combination of L+1 and L+1 bar, and so on.
Thanks.
All right. So, but what I wanted to say last is that the job of this guy is to perform translations along the cutoff surface. It's a one form because only if I integrate it over a finite stretch of the cutoff surface do I get an actual finite operator. And that finite operator should be a finite translation from the one location to the other location. And that's exactly what it does. So this exponential, for example, computes a finite translation, or this should be an L-1, by the way. This should be a finite translation by an amount which is x1 minus x2, the difference between these two locations here. And we should think of this, or a word for this, is that this is a Wilson line, but this is a Wilson line which performs a translation of the inputs along the cutoff surface. And just a final comment is that I wrote this expression here at top, but you see the first Wilson line just acts trivially on the ground state. Everything except the identity kills it. And then I have an O1, then I have this finite translation. And after applying the finite translation, I see that the whole expression evaluates to an actual two-point function as we know it. So this is a correct expression with which to compute. Any questions or comments about this?
Sorry, in analogy with Wilson lines, what would be the gauge field? L-1, or what is gauge?
Oh, this is not an analogy. This is literally, this is not an analogy. This is literally a Wilson line. You should think of this L-1 dx as a gauge field. And it's a gauge field in the sense that if I performed a closed path-ordered exponential of this kind of guy, then maybe I would get some holonomy. In this case, I won't get a holonomy. I mean, it will be trivial, but anyway, this is the kind of thing you would take if we were to compute some holonomy of a gauge field. So path-ordered exponentials are going to show up everywhere in the rest of this talk. So there really are Wilson lines.
So, sorry, but what are the gauge transformations here?
Yeah. So in this case, I mean, I'll tell you more about it in a moment, but in this case, you may be able to recognize this object as something that shows up in the Chern-Simons formulation of pure AdS-free gravity. And so, so you can really think of this as being part of the Chern-Simons formulation, in which case the gauge group would be SL2R cross SL2R, or in the diagonal case, just a single SL2R. But we will need to be a little broader than that, and I will talk about this in a moment. But for now, what I wanted to say is that I want to have an operator valued one form which performs the job of doing translations along a geodesic. And by the way, there's a notation for it which emphasizes what I'm saying, which is ds dds. So what I'm doing is I'm taking a one form which can be integrated along a cutoff. That's the ds part of it. But it's an operator valued one form. And the operator, what the operator does is actually performs the same kind of translation in the CFT, which is what I mean by the DDS. It's a vector field. Any questions or comments about that last part? No comments, so I will go on. Okay, so here's how we might want to construct our algorithm. I suppose, so now we're not in the ground state, we are in some completely general state. So, so in our general state, suppose that I have I drew some cutoff surface, and I'm literally writing the same expression that I did on the previous page here, except without a commitment to it being in the ground state. So here is some state, and I'm doing a translation along the cutoff all the way until I hit the first operator for which I will be computing an expectation value. Then I move over, but then I'm going to move over by only an infinitesimal amount, because infinitesimally further there might be another operator for which I might need to want to incorporate in my computation. And so I take this operator, and then I move infinitesimally over to the next operator, and I translate again, and so on, until maybe I have hit the last operator, in which case I perform this translation all the way to minus infinity and take the bra with the state psi. So this kind of expression that I wrote here is the same expression that I have here, except for 3 generalizations. The first one is that rather than writing 0, I'm writing psi. The second thing is that I'm writing A in general without presuming that A is going to be equal to L minus 1 dx. It's just this guy which performs these translations along the cutoff surface. Okay, so that's A. And then the previous picture was about a 2-point function, but this is just some general endpoint function. So these are the only differences from the last slide to this slide. Okay, so I wrote this expression, and the statement is that if I can construct such an A, which performs this job, it generates translations along the cutoff surface. If I know how to find A, then this is the algorithm we are looking for, or it's at least some algorithm which computes correlation functions in my state. So that's if I can find some A. That's like a lemma. If we can find A, then we have an algorithm. And then the next comment I want to make is that if A can be constructed using only CFT ingredients, then this will be a CFT algorithm, not a bulk computation. So what I drew for you here is a bulk picture, and I'm assuming that there is an A. Now in the bulk, it's kind of trivial. I can always just write a vector field in the bulk that does this. But if I have a CFT operator that performs the same job as A, then this would actually be a CFT computation here. And that's another aspect of it that I want to emphasize. Our algorithm will actually be a CFT operator. Okay, any questions about this?
But you're inserting operators in the bulk, so you have some sort of a bulk reconstruction picture in mind?
Yeah. And this is, thank you, this is about this comment. So there's also a comment about operator inputs here. So these O1s, O2s, O3s, they are some operators for which I want to compute correlation functions. But the idea is that if I want to have if I want this to be a picture of some bulk cutoff as well, then these operators have to, well, they should holographically live on the cutoff surface. And so now this is the place where I'm using subregion duality. I mentioned before that I will be using subregion duality in more than one place actually as an input. So the statement is that if in the bulk these operators here live on the cutoff surface, then in the boundary I should think of them as commuting with both rho and rho prime, where rho and rho prime are reduced density matrices for intervals whose entanglement wedges are just tangent to the cutoff surface. So, which is what I wrote here. So the statement is that if some operator commutes with such a rho, then it lives on such a Ryuta-Kayanagi surface like this. But if it commutes with 2 consecutive, so to say, 2 consecutive rows, then it lives not here and not there, it actually lives right here on the surface. And that's what I wrote here. So I'm going to assume that all my operator inputs here are satisfy this kind of condition, that they simultaneously, I'm hearing a lot of echo from somebody. So that they simultaneously commute with one density matrix, which has the condition that its entanglement wedge is tangent to the cutoff surface in the bulk, and with another one. Notice that this is a bulk condition, but it's fully statable in the CFT language. Namely, if I didn't give you a cutoff in the form of a curve in the bulk, if I gave you a cutoff in the form of just a bunch of intervals, and I would say these intervals are cutoff-sized, then for those intervals you would form rho, and then you could still use this condition. So this is a condition that doesn't make a commitment to the bulk. Okay. Any questions about that?
Sorry. So it is true that these operators can move with P and P prime, rho and rho prime, but that's not uniquely fixed in the operator because there's a lot of stuff deeper in the infrared that can use with both, right?
Oh, they are supposed to be operators that have support on just rho and rho prime, and have that property.
Ah, I see.
Okay, so good. And also, I want to say that Kabat and Lipschitz had a paper where they said that this condition can be used to essentially uniquely specify HKLL operators. So it's not, yeah. So yeah. So yeah, that's what I wanted to say. So I'm not the first one to specify to try to specify operators using this condition. Okay. Next, so the punchline of this slide was supposed to be here, which is that if we can find an A which performs this kind of translation, and if that A is constructed only from CFT ingredients, then we have specified the kind of algorithm that I have been talking about. And so let's construct A. And we're going to construct A in essentially in two steps. The first step is to use a CFT operation that I mentioned before, which is called modular parallel transport. And again, this is purely a CFT operation. However, in the bulk, it has the interpretation of mapping one RT surface to another RT surface the way that these arrows show. And so you can see that this is going to not quite do the job of A, but it's going to be useful towards it. Because if I apply this modular parallel transport, I mark it in using a notation IDV, then so it acts as a commutator I times commutator dV with rho. If I use this IDV, then I'm going to map this entanglement wedge to this entanglement wedge in such a way that this point ends up here, this point ends up here, this point ends up here, and so on. The arrows tell you what this does. This doesn't map the tangency point to the tangency point. It maps the tangency point someplace else. But it's okay. At least we have moved an RT surface to another RT surface. In the bulk, specifically, modular parallel transport is a rotation about the common intersection point if the RT surfaces intersect. So notice that this sends the X point to this point. It doesn't send it here. That's where we eventually want to go, but at least it does that. And a fuller characterization of what modular parallel transport does in the CFT language is that it transports entanglement wedges to entanglement wedges according to this formula. And so for now, what I'm going to write is 1 plus A, whatever this A is going to have the form 1 plus IDV, where this is modular parallel transport, times some other operation. And some other operation will have the job of first then taking this point and pushing it over to the tangency point. If we manage to complete this operation with one other one, which goes from here to here, then we will have constructed A. Any questions? So now we need to move here. So we need to move this point to this point. This is a motion along the RT surface. Because it's a motion along an RT surface, we know that it must be a zero mode of this entanglement wedge, which is what I wrote here. So it must satisfy a condition like this. Whatever is performing this job, I'm going to call it dP. So IdP has to commute with the entanglement, with the density matrix that I have for this next interval, next cutoff-sized interval. And so I don't have time to talk about the details of how this object is constructed, but suffice it to say that it's completely determined from dv, which is the previous thing we had. And I told you that dv is something that we have constructed explicitly in a conformal field theory. So if this dp can always be determined from dv alone, it also must be a CFT object. I don't have the time necessary to discuss how this dp is constructed in general. It also doesn't make much sense to talk about this if I didn't tell you about modular parallel transport in detail in the first place. So you will just have to trust me that I know how to construct these operators in the CFT language. And let me just say that there is some technical construction where dv can be thought of as a velocity in a certain sense, and then in that case dp is the acceleration. So you can imagine roughly what relationship there is between these two types of things, as dv and dp. Now, if I apply this new thing dp after I applied dv, then this will end up mapping the x point first to this point through dv, and then to that point through dp. That's exactly what our a was supposed to do. And so I claim that I know how to construct a, which just has the job of translating along the cutoff surface, and that the ingredients I used are purely CFT ingredients. And I'm sorry that I don't have the time and scope to tell you in detail about these constructions, but this really would be a whole other talk to talk about that. Are there any questions about this?
So if I look at the intersection point where the two RT surfaces intersect, yes. So one of the operations you're talking about is rotation around this point, right? Locally, yes. If you zoom in. The other one is translation. So yes. Is this some sort of entanglement algebra that you get that Kubat and Lifshitz talk about? Locally, the operators that generate an algebra.
The Kubat and Lifshitz mostly talk about, that one. The short answer is not exactly. That algebra related to the construction of V, actually, in a way that we probably should talk after the talk. So I can tell you a little more about it afterwards, but this slide is not terribly related to what they did. The other slide was, but we probably should take it offline.
Sure.
Okay, so now I 2 slides ago, I was making a statement, if I can construct A, then I will have an algorithm. Now I have constructed A, so we have an algorithm. And here I wrote it for you, okay? And I just rewrote it slightly in that previously I had a psi bra here, but now I put a psi bra here and I put a trace, which is the same thing here. So I just want to say, let's examine what the pieces of this thing are doing. Remember, the job of of V was to transport density matrices to other density matrices. Yes. So here I wrote and a job of P was to not transport density matrices at all. Yes. And A is IdV plus IdP, as you see from this equation. So this tells me that when I have a reduced density matrix for a cutoff-sized interval, which is the cutoff-sized interval infinitely far away, and I just apply these path-ordered exponentials before and after, then I get a reduced density matrix at other cutoffs for other cutoff-sized intervals which are not at infinity. This is the expression that I write here. Okay, this is coming from these 2 equations. So let's look at what this expression looks like if one of these input operators is the identity and the other one is non-trivial. Then it will just boil down to the trace of the non-trivial one times the reduced density matrix for the cutoff-sized interval where it's acting. Why do I say this? Well, if I make one of these to be the identity, then these path-ordered exponentials combine, and they combine to be just the opposite of this transformation. Okay. Now, so this is some unitary transformation, and this unitary, it has the job of taking the reduced density matrix for a cutoff-sized interval at the infinite, which is there at x equals plus infinity, and transporting it to the cutoff-sized for the reduced density matrix, for example, at S1. Okay. So this is the expression that I'm writing over here. And you might say, what about the tracing out of the complement? Well, once this is the identity, I can trace out the complement first. This will become rho, and this rho can then be transported by these path-ordered exponentials to become rho of S1 in this case. So the expression, at least in the case where these are just one of them is the identity, will boil down to this simple thing, which computes the correct expectation values. What happens when it is not, when none of them is the identity? So here is a slightly more complicated slide which tells you about that. And so I'm assuming that I have two input operators, and I have grouped this the expression that I get into various components. So notice that, so here I wrote this path-ordered exponential, split it into two pieces, minus infinity to S1 and S1 to S2. What is this guy? There is a path-ordered exponential from S1 to S2, and there is a path-ordered exponential from S2 to S1. And what these A's are doing are, they are supposed to transport a reduced density matrix at the point S1. This is, for example, this density matrix, to the density matrix I have over here. When I think of this object as acting not on the density matrix but on O2, it produces something that we could call the precursor of O2 that acts in row 1. Or in other words, it's the Heisenberg picture version of O2 with respect to a quote-unquote time evolution which is generated by A. So this guy is the best version of O2 that we can make by acting on row 1. That's what this part of the expression is. After I have this, I can combine it with O1 and use the expression from the previous slide. The green part just evaluates to the density matrix that acts on row 1. And now I have a density matrix for row 1 times some operator that acts in O1 times some other operator that acts in row 1, which is a row 1 version of the input at O2. So this expression might be a little hard to parse, and I'm going to display this slide when I finish the talk, so we can look at it the most, because it's probably the hardest slide to absorb. But long story short, this expression can be simplified. What this argument is meant to establish is, first of all, that this really computes correctly the CFT correlation functions as we want them. And then the second thing is that I can replace, instead of the psi-psi outer product, I can just replace it with a density matrix of some cutoff-sized region. For example, the cutoff-sized region that I would have as if I followed this cutoff surface all the way to x equals plus infinity. That's what this notation here is supposed to do. Okay, so here is the version of the final version of the algorithm, with no simplification, further simplifications, no embellishments, and no special cases. This is the general version. I write down the trace of some cutoff-sized region. Let me call it cutoff-sized region at infinity. It could be this cutoff-sized region. It doesn't matter. One of them. Yes. And then I do the following job. Move using 1 plus a little over, and then I see if there is some operator that I have to, whose expectation value I'll be computing. Then I move infinitesimally over, and I see if there is some operator. Then I move one by infinitesimally over, and I again see if there is some operator there. I move over, and I just keep repeating this until I cover the entire cutoff surface, and then I form the trace. And this is a computation of a correlation function for arbitrary inputs that live on this cutoff surface. So this is our map from operators to expectation values. It is given in the form of an algorithm. It was constructed entirely in the CFT language, but notice that it also knows about the cutoff, in the sense that these A's were not just some arbitrary things, they were specifically designed to transport reduced density matrices in my state. They wouldn't have worked in some other global state. So the A is something that knows specifically about my state and not about other states. and it depends crucially on the microscopic state through the detailed form of A, and through these equations. Now, so that's the algorithm we wanted. And now I want to ask, how would we quantify the query complexity of this object? And by the way, I will just need 5 more minutes and then we will finish, if that's okay with you.
Sure.
So I want, as we said, query complexity is counting subroutines in this algorithm. Now it's clear that the subroutine in question is just this basic object, because that's the only thing that just repeats over and over and over. One remark here is that if it's perfectly fine to represent this repeated subroutine in the form of or in our algorithm, in fact, as a matrix product state, which would be of this form. First, I have some density matrix for one cutoff-sized region. That would be just a single operator here. And then I scan along the cutoff-sized surface, and then the scanning and looking for these input operators is represented by this kind of operation. And here is where the operator inputs would come in. And then I scan, I go to the next location and take an input. Go to the next location and take an input. That's exactly the structure of a matrix product state. So if I now tell you that query complexity counts the calls to this subroutine, then that's really the same as saying I'm counting tensors in this specific representation of the state as a matrix product state. So we're again in agreement with the general philosophy that tensor networks are an example here. Now, what does our subroutine do is a question you can ask. And we've said this before, but here's a highlight again of what it's doing. It maps one entanglement sized region to one cutoff-sized entanglement wedge to another cutoff-sized entanglement wedge, and it does it in this fashion, sort of horizontally sliding along the cutoff surface. That's what A is doing. That's what A is doing. And then after moving over, it also reads one input operator for which the correlation function will be computed. So since it performs this kind of sliding of entanglement wedges, then it's natural to say that our query complexity, it counts how much I have used this A. It should be a measure of how difficult it is to map all of those consecutive cutoff-sized entanglement wedges to one another.
Sorry, and go back to the L-1, that looks more like it's just the distance between the operators. Or it depends on where you put them, not where the state is or what the state is.
Sorry, Martin, can you say again?
No, when you did the example with L-1, it seemed that the number of times you have to apply is just the distance between the points where you inserted the operators.
Oh.
And it's not related to the state itself, but to the where you put the operators.
Well, so this is an algorithm that's supposed to read off these inputs at every possible location. And so I don't know ahead of time if I'm going to compute a 5-point function or a 7-point function or a 100-point function. So I always have to keep going along here. So I wouldn't want to count the number of inputs that much. I would want to say, how hard is it to scan all of these potential locations to compute any arbitrary correlation function? And that's the proposal I'm making here.
So, but you are measuring how complicated is A, or how many times you have to use it?
Yeah. So what I want to say is that A is performing this kind of translation of it shifts an entanglement wedge horizontally along the cutoff surface. And so what I'm saying is that if I have a discrete set of entanglement wedges, then all I have to do is just count them. Okay, if I visited 7 of them, then it's 7. But if I have a continuous family of entanglement wedges, like I do in the present context, then I have to define a measure on this set of all entanglement wedges that I have visited so far. And that's what I'm trying to describe here. So if I have a measure on what entanglement wedges I have visited, then this naturally brings up a notion of a metric in the space of density matrices. And this kind of metric, yeah, so this slide is a little out of order because I should have said this in a continuum. The only notion of, the only way to quantify the use of A is by saying how many entanglement wedges I have visited and how hard was it to get from one to the other. And when I do this, I'm naturally led to a certain notion of metric in the space of density matrices. And the point I wanted to tell you, which is another point that I don't have time to talk about in detail, and I apologize that there are so many things where I just have to pull a rabbit out of a hat. This is the last one of those, is that there is an essentially unique metric in the space of density matrices, which is consistent with this equation. The technical word for this, or the technical phrase for this, is that it's the Kirillov-Konstantin-Suryon metric for the Sjökvist connection A. But I'm just using these words to tell you that I'm not making stuff up. There is a theory for it. But here is a more conceptual way of thinking about what a metric on the space of visited entanglement wedges would have to do. So we are trying to define a metric which is consistent with this equation, where A is thought of as a connection. But what A does is that it takes one entanglement wedge and maps it to another entanglement wedge. In a tensor network language, this is like saying it concatenates it takes a tensor network that lives here and it erases this part of that tensor network and it draws another part over here. That's basically what it's doing. You can imagine that in the limit where this little d rho is becoming 0, so the two entanglement wedges, the one from which I'm mapping and the one to which I'm mapping, when they are becoming almost indistinguishable, in that infinitesimal limit, the only thing that matters for moving from one to the other is just how angularly wide, what the angular width is of these crescent-sized regions between them. And this angular width between them, from the bulk perspective, from the cutoff curve perspective, is simply a definition of the extrinsic curvature of this curve weighted by the bulk length. So what I want to say is that there is a unique metric which is consistent with this equation. And then when you actually evaluate it in the bulk, if there is a bulk, then this metric ends up being proportional to the expression KDS. And so now I have my final slide and then I will stop. Our query complexity in the bulk, if there is a bulk, I just argued that it would be proportional to the integral over the cutoff curve of the extrinsic curvature times the length element in the bulk. This is what the natural notion of distance that is associated with all of those entanglement wedges that we visited in our algorithm. This is the natural notion of distance that is picked out. Now in pure AdS, this object by the Gauss-Bonnet theorem ends up being just this thing. And because minus R is the Ricci scalar on the spatial slice that fills in this geometry. So because minus R is constant in pure AdS, this appears to agree with the volume proposal. However, I want to say that when we're not in pure AdS, then this is going to be different from the volume proposal. So this is not a place to say, oh yes, volume works. Rather, I'm just saying that it agrees with the volume proposal in one of the few cases where we could tractably, in one of the best studied cases, let me just say. So I'm not saying that I like the volume proposal better. I'm actually making a completely separate proposal which shares some of the good features with the volume proposal. And now let me summarize qualitatively what I have presented in this talk. I said that this expression in the bulk gives, first of all, I want to say that it gives some measure of spatial size. So I emphasize the philosophy that we don't have to be shooting for the volume proposal or for the Wheeler-DeWitt patch proposal. If we find some notion of complexity that evaluates to a bulk quantity which is bigger when spatial sizes are bigger, then that's already good. And now this quantity certainly has that property, but how did we get it? We got it as a complexity of a state at the cutoff. It's just that it was query complexity for this state presented in an algorithmic fashion. And the algorithm involved visiting all the entanglement wedges which were tangent to the cutoff surface in the bulk. The way it was defined, however, only used CFT quantities. It didn't require a bulk input. So if I wanted to talk about it without using the bulk, I would just say a cutoff is given as a sequence of intervals like this one. Okay, then I don't have to draw this surface at all. And then the query complexity would be the distance in the space of density matrices that I visit as I go around the cutoff. Again, I can say these words without ever drawing the bulk picture here. So this is purely a CFT quantity. Okay. So I say that these things I told you about are what the dream about complexity was. It's sensitive to bulk sizes when there is a bulk, but when there is not a bulk, it's a well-defined quantity which is definable purely in the CFT language. So that's why I declare success, and that's where I'm going to stop. Thank you very much.
Thank you so much. I guess we're doing virtual. Are there any questions? I actually do have a question. So you kept insisting that this is a completely CFT quantity, but you clearly use the bulk. So is the quantity defined for holographic CFTs, right?
I do insist that it's purely a bulk quantity. So
what is
it's purely a boundary quantity.
So for example, for minimal models, what is the operator A?
We have to compute it. Although, if we're working, that question doesn't have an answer until you specify in what microscopic state we're talking about. But if we're talking about if we're working, are we in the vacuum?
Say vacuum, yeah. So
yeah, then in the vacuum, I can tell you exactly what it is, which is you take the modular Hamiltonian of a cutoff-sized region, and then you compute the derivative of the modular Hamiltonian as you change the right endpoint, as you shift it, and then as you shift the left endpoint, okay? And it turns out that, so as we are moving this cutoff.
But sorry, what is the cutoff for what is cutoff
without using the bulk language, moving the cutoff means if I'm at this cutoff-sized region and I go to another, I have to tell you about the relative rate at which the right endpoint moves relative to the left endpoint moving. So if I wanted, quote unquote constant cutoff, constant radial cutoff in AdS would correspond to shifting the left and the right endpoint at an equal rate. But I can imagine a cutoff where the right endpoint escapes faster and the left endpoint is trailing more slowly. If I have a holographic dual, that would correspond to a cutoff that's kind of going deeper and deeper in. Or I can imagine a situation where the left endpoint is moving faster, but the right endpoint is moving slower. That corresponds to a cutoff that descends from deeper into the bulk, closer towards the boundary. But anyway, I don't have to talk about the bulk. All I have to tell you is the relative rate at which the right endpoint of the cutoff-sized interval is moving relative to the left endpoint. And what I want to say is that for every one of these possible dependencies, for every such relative rate, there is an operator that we can write down, and it's related in a simple fashion to the derivative of the modular Hamiltonian with respect to the right and the left endpoint.
All right, thanks so much. Are there any other questions?
Ooh, no questions. I
actually have another question. Can't you think of this A operator in the case that there is a holographic dual in the bulk? as some sort of generating a Euclidean gravitational path integral in the bulk. You could have drawn, you know, you could have talked about the same flow for inside the bulk, right? Going from left to right or right to left.
Inside here.
Yeah, so the part of the bulk that's outside of that hole, there will be, there's a density matrix associated with that, right?
Well, there's a density matrix. There is a density matrix associated with a single one of these cutoff-sized regions. But
let me ask the question differently. There is a Euclidean path integral that I can perform that goes over everything that's outside of that hole in the bulk. Now, that Euclidean path integral could be performed by some sort of an operator in the bulk that pushes you around the circle. It's like rotation.
But what boundary conditions on the hole are we imposing?
That was actually my next question. I suspect there's a choice of boundary conditions that's being made here based on a state. I think, yeah, I'm not sure.
In some sense, these operators that were the inputs would specify different boundary conditions for such an object. So, but anyway, but the short answer to the question, have I thought about it this way? No, I haven't.
Okay, thanks so much. Okay, one last round. Any other questions?
No.
Yeah, so
yes, sorry, go ahead.
So you mentioned an operator P which moves points along the surface of the entanglement wedge. Is it like the modular Hamiltonian for that entanglement wedge? Earlier said you had an operator dp, I guess.
Yes, this one.
Yes, exactly. Yeah. So
this one is this is not the entanglement. This is not the modular Hamiltonian, but it's a zero mode of the modular Hamiltonian, as in it commutes with the modular Hamiltonian. And the reason why I know that it commutes is that if it always moves along the RT surface, that means that it preserves the RT surface. That means that it's not going to change the division between the entanglement wedge and the complement. By itself, this is not a sufficient condition to say that it's a symmetry of the modular Hamiltonian. However, it is for reasons that I can go into if I have more time. But the short answer is that it's a symmetry of the modular Hamiltonian.
Okay, thank you.
No, I was asking like a naive way to put a cutoff in a field theory just with a lattice. I mean, then it becomes like a quantum mechanical system, but this doesn't seem to be can you do something like that in that case?
You could. So I mean, the reason, so let me tell you why we are not doing it. I think this is a better thing for me to say. So if I did a lattice, then that would be like saying I'm going to have one cutoff-sized region and then another one immediately next to it and another immediately next to it, but without any overlaps. Whereas here what I'm doing is kind of sliding them slowly, yes? And the reason why I'm doing this is that I want to make contact with this constant cutoff, or anyway, some smooth, it doesn't have to be constant, but a smooth cutoff in the bulk. Whereas if I had a lattice, then that would be like having a cutoff which looks like this. It would look like the trajectory of a bouncing ball. And the reason why I say that that's what it would be is I'm taking seriously subregion duality. So the statement is that if I just have, if I say, here are my cutoff-sized region, here's another, and immediately next to it, another of the same size, then I don't have access to what's happening inside this entanglement wedge. I don't have access to what's happening in the entanglement wedge right next door. That's because they're below cutoff. But what about the kind of triangular wedge that I get here? I haven't excluded it. It seems like I should have access to it. But so in order to exclude it, I can't just say, here's an entanglement wedge and another one next to it. I have to say that the whole continuous family of them, as I'm shifting them, is all excluded. They're all cutoff-sized. And so that's why I don't do a lattice here. Did I?
But I don't understand. That's but the definition still applies, or you just don't like the example, or I didn't understand.
Oh, the definition that I gave, if it applies?
Yes.
It applies in a very, it doesn't give any nice answer that is terribly sensible. Because if I want to think of so basically I'm treating the cutoff surface as, I'm describing a cutoff surface as a collection of entanglement wedges that are tangent to it. So now if I want to work on a strict lattice, then the collection of RT surfaces that are tangent to it, it becomes sort of ill-defined because I just have a finite discrete collection of cutoff sites a discrete collection of them instead of a continuous family. For that discrete collection, well, a lot can be said about it, but it's the answer is that actually this thing is going to be infinite. So I paid a lot of attention to cutoffs, but then if I evaluate this guy on something that looks like a collection of non-overlapping cutoff-sized region, you can see that this formula will still be true. I can still use Gauss-Bonnet, but then the volume is a volume that actually escapes to infinity a little bit at these corners, and I'll just get infinity. So one thing that's problematic about the lattice is that this thing will actually give me infinity anyway. Even though I was trying to define a cutoff, it wouldn't effectively be a cutoff even in this understanding.
Okay, thank you.
The thing is that a finite, what I want to say is that holographically, a strict lattice doesn't really describe this curve, is the thing I want to say.
One last question, anyone?
Yes, I have a very naive question. With this definition of complexity, query complexity, is there any way to characterize randomness of the states, this row? If this question is sensible.
A randomness of the, let me say this, actually, maybe I'll just say I don't know, and maybe let's talk after the official part of the Q&A is over.
Okay.
Okay, thank you so much, Bartek, again for the wonderful talk, and yeah,
thank you very much. Very grateful for this invitation, and thank you so much. Oh, and I'm seeing Keiichiro is actually showing a clapping sign. Thank you so much.
Yeah, thank you. And thank you to all the attendants that came to the talk.
So it's a little bit late for Bartek, so I guess we'll let him go to bed. And if you have any other questions, we can probably send him an email and bug him later.
Well, you certainly can. I did leave a question for after the official session about the disorder. Someone asked this question, so I can. So I do have a comment about it, which is that the question of order versus disorder is all about this dv operator. So different states will have very different dv's, and if we're interested in any question about a state, most likely it's imprinted in the properties of this dv. So I just have this general answer to the question about disorder.
Okay, thank you. Sorry, could you remind me what dv is again?
Yeah, it's an operator that my collaborators and I have managed to describe purely in the CFT language, but in the bulk, it has an interpretation of a vector field that maps one RT surface to another RT surface in such a fashion that that it's effectively just a rotation about their common intersection point.
Okay, thank you.
But you can imagine that in different states, entanglement wedges are going to be very different. And so that kind of vector field will be realized in very different ways microscopically in the CFT, depending on what state you're in.
Okay, I see.